quantum computer to be built. Now, a natural question to ask is how much can we get out of these proposed error mitigation protocols in recent years? Things like probabilistic error cancellation, for instance. So this brings me to the topic of this webinar entitled Fundamental Limits of Quantum Error Mitigation by our guest, Dr. Duji Takagi. Duji is a postdoctoral researcher, fellow at Nanyang Technology University in Singapore. He has worked in topics such as quantum research theories, quantum communication, continuous variable information, quantum error correction, and quantum error mitigation. He has particularly contributed to the development of general frameworks of quantum resource theory and has recently applied these insights into performance analysis of quantum error mitigation protocols. And prior to that, he was actually a PhD student at MIT, supervised by Seth Lloyd, that everyone, I'm sure, most of you on the audience know about him, one of the pioneers of the field of quantum machine learning, if I'm not mistaken. So yeah, so it's a pleasure to have Duji with us today to present the work that he and his co-authors have recently published on the archive. So without further ado, Duji, I hand over to you. Thank you again for taking your time to come in.
Okay, thank you very much for your introduction. And thanks, guys, for the invitation as well to these very interesting seminars. So I'm Duji, and I am a postdoc at the NTU Singapore. And today I will be, sharing with you a bit about our recent work on the fundamental limits of quantum error mitigation. So basically, in this work, we are going to first introduce the general framework of quantum error mitigation and derive some results that are applied to all such quantum error mitigations accommodated in such a general framework. But I will start with some introduction so that we can be in the same page. So, of course, I don't know how many of you are familiar with those concepts, but when I say Nisk devices, so this stands for the noisy intermediate scale quantum devices. So this term was coined by John Prescott a couple of years ago, and the idea is the following, right? So of course, one of the fundamental goals in quantum information science is to build the fault-tolerant quantum computation, and that that has the error correcting codes built in it. So the idea is that there are a lot of noises that will break your quantum information. So you want to protect such a quantum information and also your operations as well. To do that, we know now that the error correcting codes are quite, good ways of, going for. But the problem is that implementing such a error correcting codes require a lot of resources in terms of the number of qubits or the accurate gates. So you need a very, very accurate gate so that this error correcting codes work properly. But now that we are in the very interesting time because of the recent technological developments, now we have started having access to a little baby type smaller quantum computers. So this is, of course, much smaller than that is required for the fault-tolerant quantum computation, which, for instance, requires 10 to the 7 number of qubits. So on the other hand, we now have access to about a 50 number of qubits, 50 qubit quantum computers. But so now this is a good time to ask another paradigm, which is now Nisk devices, which focus on the manipulating tens to hundreds of qubits without diving into such a complicated error correcting codes that would require 10 to the 7 number of qubits, and still trying to see if we can do anything useful with it. So this field has attracted so much attention recently, and people say introduced a very many quantum algorithms like Nisk algorithms known as variational quantum eigensolvers that hoping where the hope is to apply that to the quantum chemistry simulation and so forth. So now, what is the problem here? The problem is, of course, noise, right? Because declaring that we do not want to use the error correcting codes does not mean that we can actually get rid of noise. So we need to deal with it somehow. So this is how we are going to use this quantum error mitigation idea. So there's a difference between the error correction and error mitigation. And error mitigation, particularly, is designed for these Nisk devices, smaller quantum computers. But what is the difference? So the error correction usually encodes your quantum state into a higher dimensional Hilbert space. So you encode your some quantum state psi to the logical version of it, psi bar. But not only that, you also need to encode your quantum gates as well to the logical version of it. Where I write, if you're, for instance, interested in like a gate G2, then that consists of other physical gates that that applies to many number of qubits. Then these are followed by some error correction procedure that usually involve some measurement process known as stabilizer measurements, and do the measurement feedback control depending on the measurement outcomes, and you apply the quantum operations to your quantum circuit depending on such a measurement outcomes and so forth. So this, by the way, this error correction procedure itself is also noisy. So this also serves as a very big source of the noise. So, and that is why we need to use not only the many number of qubits, but also need the very accurate gates as well. So in the error mitigation, on the other hand, we do not encode our quantum states into higher dimensional space or do the online feedback control like error correction. So the difference can be seen a little bit more abstract way, where error correction uses up some space resource in the sense that you need a lot of number of qubits, so you take up some space. But on the other hand, error mitigation uses a time resource in the form of sampling cost. So what I mean by that is, so now available resource for you is the smaller quantum computers. So what you can do is to run these small computers so many times that you can extract some interested information about your physical systems. So there's a trade-off here between the time resource and the space resource. So this is why looking at this time resource, how many samples you need to realize the reliable computation is a very important figure as a merit in the Nisk devices and also error mitigation protocols. Okay, so motivated by that, there have been various types or ways of doing these error mitigation protocols, and people keep proposing these ideas like this. So starting from the probabilistic error cancellation method, so like these are just examples of the error mitigation protocols proposed so far. But I don't, unfortunately, I don't have full time to dive into every single idea. But the point of this slide is just to show that there are many specific error mitigation protocols that are individually proposed and individually analyzed. So for instance, if you take a probabilistic error cancellation, then you analyze this performance. And noise extrapolation, again, you analyze this performance. And actually, we're going to take a look at several of those later in more detail. But we can now ask, looking at this list, we can now ask these following fundamental questions. So, how long should we do this? So, when is a good time to stop, right? Because if we're not sure, like the ultimate goal of this, journey, then we should just try to keep proposing these error mitigation protocols forever. And so the problem here really is that there's no way of telling the optimality of a given error mitigation strategy. So if you're given some, say, probabilistic error cancellation, is there any room for improvement for such an error mitigation? Then if there is, it's worth thinking about proposing another way of error mitigating your system. But it's also quite possible that these error mitigation protocols inherently have the fundamental limitations, so that we can never achieve the desired level of such a protocols to mitigate errors. So this is now the value of the theoretical investigation comes in, then to figure out sort of the ultimate limits, fundamental limits of quantum error mitigation protocols in general. So this problem can be addressed by asking the following questions. So is there any unified way to characterize their performance? So, but to do that, we also first need a general framework for the quantum error mitigation, because otherwise we cannot get any results, right? So like we should first fix some general framework, then try to get some results or theorems that are applied to all the error mitigation protocols accommodated in such a framework. Then this general framework should be the one that includes these list of the error mitigation protocols as special cases, but also possibly include other error mitigation protocols that are yet to be discovered. We just don't know what they are, but what in the future, maybe people come up and propose another error mitigation, but hopefully our result can be also applied to such a new error mitigation strategy. So then our results are really like that. So like we have some general results that can also accommodate those cases. So yeah, to do that, let me first start with this general framework for the quantum error mitigation. So let me go step by step. So firstly, the standard goal for the Nisk algorithms, many Nisk algorithms have a goal of estimating the expectation value of some quantum state psi. So this suppose that A is a Hermitian operator. So this is a physical observable that you're interested in. For instance, this is a Hamiltonian. And suppose that this psi is the state that you're interested in. This might be the output state from your quantum gate or the quantum circuit U. Then what you do, I mean, in the noiseless case, if there is noise, there was not noise, then what you do is to make a measurement, right? So you measure the observable A and extract outcomes and try to get the expected value of such a measurement outcomes. So you may see these kind of distributions, and you try to estimate your expected value of such distributions, and this should correspond to the ideal expectation value. However, like we have noise, so this is a problem. And so if we have noise, what we can do in general is that we collect the number of copies of such noisy states. Then we apply some operations on it so that we can extract some information, which is this trace ASI, the expectation value, by applying such a quantum process and also classical post-processing operations. So this E1 to En are the effective noise channels that map the ideal quantum state psi to the noisy version of them. So then these noise channels might be different from each other in general, because you could also tune the level of the noise in your noisy circuit. But anyways, like you have this large n number of copies of the noisy states that you're interested in. So this P is some quantum process. So this might involve some additional gate or quantum measurements, which is important. Once, like if you make a quantum measurement and you get some classical measurement outcomes. So so this P is, so this P involves everything, right? So like you might apply some additional quantum process, and also you terminate that process with some quantum measurements, and you get the classical measurement outcomes out of that. And you will get some estimate, EA, of the expectation value of trace ASI. So this EA is a random variable that serves as an estimate of the expectation value of trace ASI. So then the same thing. So you run this protocol so many times that you try to estimate the expected value of this distribution. So like each round might get some measurement results. Then you try to estimate the expected value of such a distributions. So this is what you can do in the noisy case in general. And to see the figures of merit, we have a couple of things that we can look at. The first one is called bias. So bias is the difference between this true expectation value and the expected value of this random variable that is coming from this noisy process. And so this comes from the estimation theory, which they also use the word bias. And bias is basically the deviation that you have in your estimator and from the true expectation value you're trying to estimate. And you might also have different distributions from the true distributions. You might have some spread over these distributions. So this is another parameter that we're going to look at, and we are actually going to take a little closer look at these two, quantifiers later. But this is the general picture in a nutshell how this quantum error mitigation works.
Excuse me.
Yes.
Have a question from Amir.
Yes.
In A, is the measurement a joint measurement observable? And in B, are we seeing single Pauli observables?
So can you repeat the first question again?
In A, is the measurement a joint measurement observable?
So A is this A observable is anything. Then this A is observable that applies to this your quantum state psi. So if this psi, so this wire, by the way, does not necessarily represent your qubit, but if you're interested quantum circuit, for instance, BQE circuit has like k qubits, then this might be a k qubits wire. So then this A is a joint measure. Okay, if you say joint measurement, there might indicate some terminologies, but this A is some observable that applies to such a k number of qubits. But this is a single observable that can be anything. So that also answers the second question. That might be different from Pauli. Yes.
Thank you.
Great. Thanks for a question. And okay, now, so we introduced this quite general framework of the error mitigation. However, we can do a bit more than that. So in reality, we could also have some limitations because of the experimental access or even like fundamental reasons. This quantum process might have access to only up to q number of inputs. So this large q is some number that depends on the situation. So in that case, this quantum process P can only maintain your quantum coherence or entanglement up to q copies of your inputs. So in such a case, it makes sense to consider. So this is pretty much a general thing that you can do is to consider this kind of picture, where suppose that this large n is the multiple of q and some number large k, then so I divide this this big quantum process into the large k number of quantum experiments. But each experiment then involves the large q number of inputs there. So so then what's really happening is that each of them constitutes each quantum experiment. Then this within this you can now maintain your entanglement and so forth. And this is a quantum measurement. But you cannot extend this to the whole like large n copies of it. Then now you can rewrite these effective noise channels into this form, where this superscript refers to the experiment. So this is the first experiment up to the large k experiment. Then my subscript refers to the level of the input. So this is the first input to the q input. then they might be different from each other in general. Then they are the quantum measurements. So I take the measurement outcomes from them. And then what we can do is to apply the classical post-processing there. So I take the measurement outcomes from each experiment here from I1 to, there is some typo here. This small n should be large k. So this is I1 to Rk. Then I use these as an input to some classical function, and so that I output some estimation for the expectation value ASI. Then I repeat this a large m times, so that I take the expected value of such random variables, hoping that this expected value is going to be close to the expectation value trace ASI. So I call it QK error mitigation protocols. So because I take the Q inputs into one experiment and I have large K number of experiments. So this is a QK error mitigation. So now if you're given, if the QK error mitigation is a large class that accommodates many, possibly, many possible quantum error mitigation strategies as special cases, and that kind of accommodate those specific mitigation protocols. So this is our general framework now. Then let's take a look at some examples here. So I, took up like 3 examples here. So the first example is a probabilistic error cancellation method, which I'm going to take a little more closer look later. So what happens in this protocol is that suppose that you're given some erroneous state E of psi, then you apply some quantum operation that is sampled from the set of basis operations. So the B stands for basis operations. And after that, you make a measurement here and do some classical post-processing, depending on the measurement outcome and also which operation you applied from this basis operation set. So this was introduced in this paper, and what we can see this specific example as as an example of the 1-1 error mitigation protocol. Now, where Q is 1, because I have only one copy to this one quantum experiment, and I have also only one experiment here. So that's why this is the 1-1 error mitigation. The second example is known as the noise extrapolation method or Richardson extrapolation method, introduced also in this paper and another paper as well. So the idea now here is that, you're given some noisy state, but to reconstruct or to guess your noiseless case, you prepare the different noise levels, which can be prepared by yourself. So by increasing the noise level, basically. So then you prepare these set of noisy states so that then you basically make a plot for each noise level so that you can extrapolate the noiseless case by looking at these data. So that is why I make a measurement at the measurement at the end, and I take these classical measurement outcomes, then apply the post-processing there. So this is known as R's order noise extrapolation. So this is now the example of the 1R+1 error mitigation protocol, where the input to a single experiment is just one copy, but now I have R+1 different experiments. On the other hand, the recent proposal includes the virtual distillation protocol proposed in these papers. So the idea is now for the virtual distillation is that given some noisy state, so you collect some number of copies of such a noisy state. So these are the identical noisy states. Then I apply some coherent operation over these copies of the noisy state. So this D is known as a derangement operations in these papers. But Then I make a measurement at the end, and again do the classical post-processing. So this is an example of the R1 error mitigation, because I have now the R copies of these noisy states, but I have only one experiment. Then I do it many times. Yeah, so these are some examples. So this is to recap how this error mitigation procedure works in general, right? So like this is a QK error mitigation protocol, and what we do is that we get these measurement outcomes and apply some classical function and do this large M times, right? So repeat M rounds to get the set of estimates from small m is 1 to large M. So suppose that this EAM is the classical single shot estimation for the small m's round of the for the protocol, and so I take the expected value of such a random variable after this large m repetitions of such rounds. So this is my estimate for this expectation value of trace A psi. But now we can look at the two figures of merit here to sort of quantify the performance of error mitigation protocols. The first one is the bias function. So I already mentioned that before. So this is the difference between the expected value of the random variable for each estimate and the true expectation value that we are interested in ultimately. So this bias function sort of corresponds to the situation where we have m infinite. So if we have the infinite number of copies that we can run the infinite number of rounds, then we will be able to get such an estimate that coincides with this expected value of this EA. But still, you might be deviated from the true expectation value A psi. So this is the bias function. And on top of that, we also have the statistical error from the shot noise. Then this is the difference between this estimation after the repetition, large M repetitions of these rounds, and expected value of the random variable. So this is the combination of these two. But now that we are interested in sort of getting the general results that evaluate the performance of the arbitrarily given error mitigation protocol, right? Then suppose now note that this bias function is an inherent property of the given error mitigation protocol. So if you're given error mitigation strategy, then this bias function is already determined by your definition of a strategy. So what we can get as a general result is to have the relation between this repetition number m and the statistical error that we're going to have. So this is the direction that we're going for. And the question we're asking now is how many samples are needed to ensure the statistical error delta, and how can we phrase this and connect this to the property of the error mitigation protocol, encompassed in the QK error mitigation. So this is now, you can bring up the estimation theory and use this half-length inequality, which says that the number of samples large M that ensures the error, the statistical error within delta with probability 1 minus epsilon is lower bounded in the following way. So this might look a bit complicated, but the point is that firstly, this delta and epsilon are kind of arbitrary numbers. You can just fix whatever you want depending on your needs. But what's important here is this delta EA parameter that describes the property of your quantum error mitigation strategy. And that serves as a lower bound for this sampling number. That is why we are interested in that. Then this delta EA, what was that? So I again also briefly mentioned that in the previous slide. This is the spread between the maximum possible value and the minimum possible value for the classical function that we consider in the error mitigation strategy. So if you remember, this plot that I had in the previous slide. So this is the distribution from the error mitigation strategies. Then I define this as a spread. So what's happening really is that I have now expected value of this distribution. So this is EA expectation. And this is the noiseless distribution I would have from the noiseless quantum circuit. Then, so this was the bias, right? So this is the difference between the true expectation value and expected value. And also, if I, make a guess, make an estimation from the large M number of samples from this distribution, and I would probably guess, for instance, this, and this is the, another error that is coming from the statistical error. So so this, relation sort of establishes a relation between this delta EA and delta and this probability and so forth to this necessary sampling numbers. Then we're going to connect this delta EA in the form of in the form that we're going to see later. But another final comment is that now we also need to introduce a little bit different the variants of these quantifiers, because the idea here is that error mitigation should work for any observable A. So it makes sense to define the maximum bias and the maximum spread as the the worst case scenario by taking the maximization over all the observables A. Whereby I also normalize this observable A, which makes sense because if you just if you don't normalize, then you can never assess the performance of some error mitigation protocol itself. But so that's why I normalize this. But basically, I take maximization over such observable and call it maximum bias, and also call it maximum spread. So now we can turn our question into the following. So what is the relation between this delta E max maximum spread and B max maximum bias? So remember that this maximum spread corresponds to the sampling cost, and B max is the bias, so which quantifies the performance of error mitigation, the reduction in the error. Then this is our main result. So we can get the following relation, where for the arbitrary QK mitigation protocol, formalized in this picture, then we will have this general inequality that serves as a lower bound for the maximum spread. Okay, so this is a relation between the maximum spread, maximum bias, and something else. Then let me mention what this something else is. So firstly, this L is this. All right, so this E is the noise effective noise channels here. So this is basically the noisy state. So this is a known noisy state. And this D trace and DLM are known as distinguishability measures in quantum information theory. So this D trace is the trace distance, which refers to the distinguishability in a situation where you're given any quantum measurement. So the operational relevant setting is that you're given state rho and state sigma, and you're asked to distinguish between these two states by making quantum measurements. And the success probability of guessing it correctly is characterized by this trace distance. And the more further apart these two states are, the better success probability you will have in this such an operational task, which makes sense. And this DLM is another type of distinguishability measure, which might be less familiar to you guys. So this is a local distinguishability measures. So this is still the distinguishability measure, but in a situation where you're only given the local quantum measurement. Then what I mean by local, so like if you say local, like you also need to define what the local subsystems are. So my local subsystem here is this each experiment. So like I take this quantum subsystem system as a subsystem, local subsystem, and so that is why I have the large K number of subsystems. And this local distinguishability measure is defined with respect to such partitions. So the use of this, yes?
There was another question from Amir. What if we do not know or cannot calculate the true expectation value? That was from a few slides back. Sorry.
Okay, I'm not sure exactly where he or she was pointing out. However, it is usually the case that we do not have access to the true expectation value because this is the sort of the aim of this error mitigation, right? But we need to still estimate the performance of the such an estimation procedure theoretically. This is analogous to quantum metrology or some estimation task where you're trying to guess or estimate something. Of course, you don't know the true value, but you want to assess the performance of such estimations. I hope that answers the question. Okay, and I'm sorry, guys, because I cannot see the Q&A panel because of the full screen mode. So just feel free to speak up if I don't fully address your questions. All right. And yes, so this use of this local distinguishability measure reflects the hybrid nature of the quantum error mitigation strategies. So what I mean by that is the quantum error mitigation is really using the quantum resource and the classical resource in tandem. So you apply some quantum measurements here, but after that, you apply some quantum computation. So everything quantum happens here, then after that, you do the classical. So like this local distinguishability really, separates this quantum part and the classical part, in a sense. Okay. And the interpretation of this inequality can now be the following, right? So this noise channel can sort of decrease the distinguishability measure. So, but the more this noise channel decreases this distinguishability, the harder it should be to reconstruct the true expectation value. So this idea can be more clearly seen by this corollary, where I just apply this Hofstad's inequality from to the previous result. So this is the precise relation between the sampling cost m and the the estimation error. So this is for the arbitrary QK mitigation protocol. The number of samples m required to guarantee the estimation error of at most b max plus delta with probability 1 minus epsilon satisfies the following relations. So again, if this noise decreases this distinguishability so much, then you need to inject more sampling costs, which makes sense intuitively, but this result now formalizes our intuition in this way. So you can see this as a trade-off between the sampling cost m and the systematic error b max. So this is the one where we're seeing it. And another way we're seeing it is that we have now the relation between the sampling cost and the distinguishability, which is the information theoretic measure. So, and it is, as far as I know, it's kind of the first time to, bring in this information theoretic measure to assess the performance of quantum error mitigations. And one note, though, is that one can replace this local distinguishability measure with the trace distance without any problem. So like you can just you can replace this with trace distance, and it should still serve as a valid lower bound on the sampling cost m. Then this is because this trace distance measure is the upper bound of the local distinguishability measure. Kind of trivially, because this local distinguishability measure allows you to only use the local measurements, whereas the trace distance allows you to use the all quantum measurements. So this might give you a little looser bound, but this might give you more handy expressions. So, the proof is a bit involved, but, I can tell you some intuition behind the proof, like how we approach this problem. So this starts from asking this, the fundamental questions. So the quantum error mitigation is a procedure that, mitigates noise effects, right? So, but does this mean that the quantum error mitigation help distinguish two noisy states better by doing this? The answer is actually no, because quantum error mitigation protocol itself is a quantum channel. And the quantum channel, the CPTP map, completed positive trace, trace preserving map. So these quantum channels should respect the data processing inequalities, saying that application of quantum channels do not increase the distinguishabilities. But so how do we understand this, right? Because error mitigation should really mitigate the error effect. So what's happening? So what's happening here is that suppose that you take two quantum states, psi and phi, and suppose that this expectation value of these two states are, sit here. But because of the noise effect, these, expected value, is shifted inward like this, for instance. But error mitigation can now separate these distributions apart from each other so that we can get a better estimate by taking the expected value of these two distributions. However, data processing inequality says that this should not increase the distinguishabilities. So this leads to the broadened distribution between these two distributions. And so that is why this overlap itself should be increased because of the data processing inequalities, so that everything makes sense. So this now gives you the idea of the fundamental trade-off between how much error can be mitigated, which is the bias reduction that is represented by these arrows, and also the increase in the spread that should respect the data processing inequalities. And these broadened distributions now give you the fundamental sampling overhead. All right, so how do we apply these insights, the general insights? The first application is to the layered circuit, which is the standard class for the quantum variational eigensolvers and so forth, which is heavily used in the Nisk algorithms. So suppose that we have the large L number of layers of the unitaries, followed by some error models, local depolarizer nodes. Okay, and so now your task is to mitigate your errors by applying some error mitigation protocols. So which means that for some, you can now choose some certain Q and K and apply some QK error mitigation protocol. So this noisy state now can be regarded as one copy of your noisy state in this framework. And now we can apply our general results to this situation. In particular, we can get that for the arbitrary QK error mitigation protocol, this relation is always satisfied. Where, again, like this left-hand side corresponds to the sampling cost, and right-hand side, if you look at this right-hand side, then this is something that grows exponentially with respect to the circuit depth. Circuit depth is a large L here. So what I mean, so like I'm talking about this factor. So this means that once if you have large L, like a long depth of the quantum circuit with a long depth, then you will this will incur the exponentially many sampling cost. So because this also gives you the sampling cost. So yeah, I mean, this is intuitive, right? Because like if you have this very non-shallow, like a deep circuit, then your quantum state is degraded and degraded. So this leads to the degradation of the distinguishabilities. So this degradation of distinguishabilities now through our results give you this maximum spread, and that is related to the sampling cost, exponential sampling cost. Then, the analogous result was also recently shown by this paper by the group by Patrick Coase from the quite different approach. Okay, another way of kind of using this is going back to my initial question. How do we see some protocol is optimal, right? So then we can kind of demonstrate that using this probabilistic error cancellation method. So by seeing this is an example of 1-1 error mitigation protocol. So probabilistic error cancellation works as follows. So you experience some error channel E, and you're trying to apply some inverse channel, E inverse. But this E inverse might not be the valid quantum channel CPTP map, but this could be this is a linear map still. Then this linear map can be expressed by the linear combination of some basis operations Bj if you choose the right Bj. I mean the set of basis operations using this the real number Cj. So since this is Cj is a real number, so this can be also a negative number. So this is an important point. Then I define the absolute value of these coefficients and the sum of them to be a gamma factor here. So the probabilistic cancellation goes as follows. So I apply the basis operations Bj to the noisy state E of psi with probability Pj defined in this way. So this is sort of the artificial probability distribution that you can create from this set of coefficients Cj. And you measure this observable A to get some outcome Aj. Then at the end, you multiply each outcome by the gamma factor and also sign of such a coefficient Cj. And if Cj is, for instance, a negative number, the sign Cj is -1, and otherwise it's +1. And I take the average by running this protocol many times. Okay, so then this is our figure of the probabilistic calculations. Okay, so in our context, right? So this what is the spread of this probabilistic calculations? So this spread is precisely this gamma factor, because I apply this overhead constant gamma, so that contributes to broaden your distributions. Then this comes into play in the form of the maximum spread in our framework. Then this gamma factor was studied previously as the fundamental sampling cost for the probabilistic cancellations. And in particular, to get the ultimate capability of the probabilistic cancellation, you need to take the minimization over all feasible basis set of basis operations. So I call it the gamma optimal. So in other words, this gamma optimal characterizes sampling cost for this probabilistic error cancellations. Okay, so this was the introduction of the probabilistic error cancellation in the context of our framework. But now let's look at the specific noise models, right? Then see how this probabilistic error cancellation performs. So if you're given a dephasing noise like this, then the probabilistic error cancellation again is an example of 1-1 protocol. Then we can actually get that this optimal gamma can be calculated as 1/1 minus 2 epsilon. So this was calculated in my paper. And now, let's forget about this probabilistic error cancellation for now, and let's calculate our general bound, the strategy independent bound that we got in this work. So what is the bound for the unbiased 1-1 protocol mitigation protocols? Okay, then this was, I calculate the bound here I derived in the previous slide, and you can easily get the lower bound for this as a 1/1 minus 2 epsilon. So this is, now if you look at this previous expression, this is the same as this. So this lower bound is achieved by the probabilistic error cancellation performance. So this is a way of seeing that the probabilistic error cancellation is actually optimal with respect to our figures of merit for this noise model. And if you compare to any possible unbiased 1-1 protocols, you can say that this probabilistic cancellation achieves this optimal performance. So of course, you can now look at the different noise models, like a depolarizing noise. And again, you can calculate this performance of probabilistic cancellation in this way. But now, you can also get the strategy independent bound from our work, and I can get 1 over 1 minus epsilon for this. And there is a slight difference between that, but difference is not very big, the order of epsilon. So this is like a nearly optimal, but still leaves the possibility for a better protocol to exist. So in this way, if you look at this, even if there's a gap between these two bounds, like a general lower bounds and some specific bounds, you can use this as an indicator for the room for the improvement, and that gives you the motivation to look for other better error mitigation protocols. But if some protocol already saturates such a bound, then this is the best one that you can prove. And we can also do some numerical simulations like this as a toy model using this hardware efficient ansatz. And you can see that this strategy independent bound we got correctly serves as a lower bound for the probabilistic error cancellation performance. And also, as we saw in the previous theorem, this estimator is also growing exponentially with respect to the number of layers. Yeah, so this was pretty much it, and let me quickly summarize. So in this work, we introduced a general framework for the quantum error mitigation, so that we are going to so that we can talk about the performance in the unified way. And we actually derived a trade-off bound between the sampling cost and the bias in terms of the information theoretic measures, particularly using the trace distance and local distinguishability measures, and connected the degradation of the that distinguishability to the sampling cost. And we used our bounds to show that the error mitigating errors in the layered circuits, such as in the variation of quantum eigensolvers, requires exponentially many samples with a number of layers. And using this, we showed that the probabilistic error cancellation is optimal, probably optimal for a certain error model. So I consider this work as sort of starting point of this new program of the general theory of quantum error mitigations. And it will be interesting, for instance, to apply our framework to many other error mitigation protocols, or when somebody comes up with new protocols, how we can apply our general results to that, and especially recent hybrid proposals that combine the multiple protocols in the unified framework, and how does that perform? And that's an interesting question. And also looking at the relation between the noise pre-knowledge and spread bias bound is also interesting. So there's another important factor in the error mitigation, that what kind of information or the knowledge you have about the the noise model. So for instance, the probabilistic error cancellation requires you to know the error models. On the other hand, the extrapolation method does not require to know such an error model. So there should be a more intricate relation between the pre-knowledge and also spread bias relations. And it is also interesting to look at the other possibilities outside error mitigations that use the combination of quantum process and also the classical post-processing, and then see if we can get the similar fundamental relations between the sampling cost and maybe distinguishability measures and maybe something else. And relation to normal confidency is also interesting. So if you're trying to measure the amount of normal confidency, one of the ways to do that is to use the trace distance and see how much trace distance you can gain by the information backflow. But now we introduce this trace distance to the error mitigation context. So it'll be interesting to look at the relation between the normal confidency and quantum error mitigation in our framework as well. And finally, it'll be insightful to look at the relation to the theory of error correction, which is quite a complete theory already. And especially in these days, we have now the Nisk era. but ultimately we do want to go to the error correction regime. So it would be key to understand the smooth stroke from the error mitigation regime and error correction regime, and for that, having more established general theory of error mitigation seems to be required and useful. Yeah, that's all I want to say here. So thank you very much for your attention.
Yes, thank you so much. I hope I'm still online. Sorry,
Yeah.
guys, my network decided it seems to be Tuesdays. That's why I normally avoid to organize stuff on Tuesdays if I can. Instead, we do it on Fridays. But yeah, thank you so much. It's very insightful to me, certainly. Though I missed some parts of it, but I will definitely rewatch it again and go through. It's definitely interesting. Having a general framework in order to assess, different error mitigation protocol is definitely very handy, even very handy for those guys on the thing, especially the software engineers. If you can build software tool to help, aid with that will be even much more interesting for researchers. So yeah. My that has somewhere on the chat or something.
There was a couple of questions that were answered by the speaker.
Okay. So I guess I don't see any other questions, so I dare to ask one while I give time for others. Yeah. So for me, this question is, about your I won't say your magic ball crystal or crystal ball or something. But let's say which of the looking at the ecosystem at the moment, which of the error mitigation protocol that you are more hopeful about? I mean, you talk a lot about the probabilistic error cancellation, but in the sense, which one has more potential, you think, to narrow the gap between mitigation until we are between the error mitigation and error correction as we as the devices get better and better?
Yeah, so I think that this hybrid approach had some potential. So what I mean by hybrid approach is that there's some recent work trying to combine the probabilistic error cancellation and, for instance, noise extrapolation. So the problem of the probabilistic error cancellation, although it is pretty efficient, is that, again, you need to know some information of the noise. On the other hand, this noise extrapolation is noise agnostic. So it's kind of, natural trying to combine those two and even like more techniques at the same time. So like people are now going to direction recently to combining many stuff in a unified way. Then, for instance, like one recent paper addresses the subspace expansion, which is known as one quantum error mitigation, but they sort of propose a generalized subspace expansion in a way that includes almost everything. Like it's like a wide class of the error mitigations, and so I think those combinations, certainly including the probabilistic error cancellation ideas, but also noise extrapolation and virtual distillations, those are quite hopeful among the error mitigations. However, I do want to also point out that it's quite possible that error mitigation doesn't work at all at the end. Then this work has such a message too. We might want to be a little cautious about heavily relying on the error mitigation techniques, because we will be seeing some exponentially bad performance in the error mitigations, and this is one of the points of this work. So of course there should be many ways of get around that. So that is the the hopeful future directions that people.
Okay. I seem to disconnect a little bit. You can still hear me, right?
I can now hear you.
Yes. Does anyone else has any question, advice-wise? especially the young audience from the class, about career-wise stuff you would like to share? Does anyone have any question? Well, I guess I will ask on your behalf. I'll pretend that I'm one of the things. So, if you were a young at this stage, wanting to pursue the same line of research as you, what practical advice would you give them as a thing, that you think they should you wish, at least, especially stuff that you regret someone have told you before you went to grad school and now you are a postdoc?
Yeah, I guess I'm still looking for the answers for that, I guess, because it's a very hard question. But what I can say is that first of all, I am coming from outside of this Nisk stuff, because I usually work on the stuff that is quite different from that, quantum resource theories, which is a little bit more fundamental information theoretic way of looking at what is the quantumness underlying the quantum mechanics and what is the way of operationally understanding it. But now, I would say because of this pandemic as well, I got stuck in Japan for a while, and I got a privilege to work with some startup company called Kunasys based in Tokyo, and that's how I kind of started working on it. But having this different mindset was quite helpful for me. And for instance, the work on the probabilistic error cancellation I also cited in the slide was connecting the probabilistic error cancellation and the resource theoretic ideas. And this was a kind of interesting connection for me, and it was also useful to have. And this general framework of the error mitigation was also inspired by my work on the general resource theories, where there is a similar situation in the quantum resource theories. The quantum resource theory is basically the generalization of the entanglement theory. So like entanglement theory, you have, the amount, quantifying the entanglement and what kind of entanglement manipulation you can make by using the LOCC and so forth. But this idea was generalized to a larger class of the quantum resources. So this is the idea of quantum resource theories. But now I just do the same ideas for the quantum error mitigations. So not only looking at the specific protocols, but looking at it more general perspective. So the message I can extract from my experience then is that having the different expertise and interests might help you in a little unexpected way. So I would just encourage you to pursue what you feel very interested. And I guess it might not have to be these Nisk devices. It might be very foundational ones, but at the end, you might come back to this practical business. So and having a little different perspectives from the mainstream would be also quite important, I think.
Yeah, absolutely. Thank you. I'm sure the audience are taking the note of this. Is very very important. I mean, people come from different backgrounds and this type of stuff. So there isn't a unique path. Obviously, you can always inspire from someone else's path, but in the end, you are right from the stuff that you just said at the end. Was there any other question on the thing? Please, guys. I know we are running like 15, even though we started a little bit, late because of my technical glitch on my side. Does anyone want to say any final? Yeah, go ahead, George.
Nothing recent in the chat, but please ask any questions.
Maybe about the future of the industry. Where do you see in your thing? Again, this coming with the thing, but in the overall, similar to what I was asking about the error mitigation protocols. Let's put it in the context, in a broader context of the industry and these things. Do you think we will achieve fault tolerance in the next 10 years?
This is like one of the most popular but hardest questions to answer, right? Okay. I also worked on quantum error correction a bit earlier, and which uses a lot of qubits and complicated quantum wiring and stuff. And I really felt, I mean, I enjoyed working on it, but I really felt that it was really on the sheet of paper. It was pretty easy to draw a wire as a qubit and connect a CCZ gate or CCCZ gate and so forth. But for torrent, it's very hard. It's very hard. So I don't think it's sensible to even guess if you can realize that in 10 years or so forth. You will, I mean, we do not still have a good idea of like which platform we should use, right? Should it be the photonic system? Should it be the superconducting system? And if you go for the photonic system, we need to use another way of error correction, GKP code and stuff. So I feel that there should be also this theoretical breakthrough too there, but those breakthrough cannot be expected. So I don't really know, but still, like I feel that having these theoretical discussions in research is valuable in any case. So in a sense, I don't care. So and I just like if it's built, and that would be great. But otherwise, people can still get the meaningful results. So it's okay too.
We do have a question in the chat now from Fernando asking, what is the Markov probability? I think he means what is the Markovian condition, but
okay, I can. So before that, I can also see a question from Bob, I guess, asking if I have actually applied these techniques to a working quantum computer, or is that homework not there yet? So to answer that, I haven't applied these techniques to a working quantum computer, although I mean, the answer is no. So like what you would do is to get the specific noise models. But once you get the noise models, then you can just like put the result into this framework. So then you can just play around with it. But we haven't we haven't done that yet. And what is the Markov probability? Okay, I'm not sure if I understand this question fully. I mentioned no Markovianity, which is different from the Markovian stochastic dynamics. Okay, this is related, of course, the stochastic Markovian dynamics, but no Markovianity is basically that your quantum information can come back from the environment by the correlation, the memory effect that the environment has. So this actually can help you error mitigate. So there's some work talking about the relation between non-Markovianity and quantum error mitigation, and actually help reduce the sampling cost there. So I just like raise this point in a way that it would be interesting to have the further study on that.
Okay. Yeah. So I guess I'm still on. I was cut off for a bit. Is there any other question? Am I still on?
You're still with us.
Okay. Yeah. So if there is no other question, I know it's too late in Singapore, so we don't want to take much of the sleeping time from our friend. So if nobody has any questions, we thank our illustrious our friend for coming and giving this very insightful talk about this very interesting framework. And I actually, by the way, for those of you who are, as I was mentioning before at some point about building software tools to help implement this type of stuff, to help researchers, assist researchers. So maybe this is an interesting challenge for those of you looking to build something open source and these things. I know, for example, there's this open source project called mitigation, which actually has implemented the probabilistic error cancellation, and I believe they also have implemented the zero noise extrapolation protocol into it. So we are seeing more and more tools being built and these things. So I hope this stuff like this can motivate some of you, especially those coming from software engineering, to go and contribute with something to return to the researcher, because it benefits all of us if researchers have software tools to be able to do things with their stuff. It helps us, all of us, because the pipeline of new ideas, from ideas to implementation become faster. So yeah, so thank you so much for coming and being with us, Digi.
Thank you very much. Thank you.
And yeah, we look forward to having you back again. Hopefully, once especially when you add more protocols, for instance, So yeah. So thank you so much.
Thank you very much.
George, thank you so much also.
Oh, something came up in the chat.
For
Oh, it's thank
covering me.
yous. More thank yous in the chat.
Okay.
Sorry. The chat is scrolling very slowly for me today, so my apologies to Bob too.
Yeah, it's okay. Thank you. So Duji, thank you so much again for being with us, for taking your time this late in your in Singapore, and yeah, we look forward to seeing you again. Thank you.
Yeah, thank you for having me.
Okay, thank you everyone, and thank you for being with us, especially the ones waking up early or staying too late. Thank you so much, and have a good day.
All right, thank you.